Welcome, and let us continue discussing about bonding part 2. And today we're going to discuss the valence bond theory. All right. So before that, let us discuss the difference between valence bond theory and molecular orbital theory, so that you know you can follow the discussion and understand why do we have two theories which actually complement each other. Okay. So the first theory is valence bond theory. Okay, the principle of valence bond theory, that is a bond between two atoms, is formed when a pair of electrons with their spin pair is shared by two overlapping. Okay, so in valence bond theory, the covalent bond is viewed as an overlapping of orbitals, atomic orbitals, from each atoms, one orbital from each of the atoms joined by the bond. So if you can imagine that the orbitals, okay, like this one, for example, you have hydrogen gas. So one atomic orbital, one s from the first hydrogen and another one s from the second hydrogen. This is originally what we call as atomic orbital for hydrogen 1s, hydrogen 1s. And when the covalent bond is formed, electron is shared between these two hydrogen. Okay, you can see the overlapping of the atomic orbitals, forming a new orbital called hybrid orbital. So this is the basis of valence bond theory. It is an overlapping of atomic orbitals between the atoms in a compound, and the overlapping will form hybrid orbital. Right? The atom will position itself so that maximum amount of orbital will overlap. This will minimize the potential energy. Okay, so let us look at the other example. For example, you have 1s orbital from hydrogen. In order to form hydrogen fluoride, HF, okay, you have what we call, hydrofluoride, HF, and then you have 2p orbital, okay, electron in 2p orbital from fluorine, and this will overlap. You can see 1s overlap with 2p, and electron is shared here, and you have what we call as a new hybrid orbital called SP, right? Okay, so this is another simple diagram showing that combination of 2s and 2p, which will form a new orbital called hybrid orbital, sp. And even the shape now is different than the original 2s and the original 2p. Okay, so let us look at the beryllium hydride, okay, BeH2. Okay, so 1s from each hydrogen, you can see from the left side and the right side. Okay, in order for beryllium, okay, to provide a space to share electron, okay, you can see that the original atomic orbital of s and p is changed into sp hybrid. So therefore, the electron or the atomic orbital from hydrogen can overlap with the sp hybrid orbital, forming this new hybrid orbital between hydrogen and beryllium. Okay. Now, before we move on, let us look at this video because it is important for you to understand the difference between these theory before we can discuss the MOT. Okay, so we have discussed a bit on valence bond theory.
Molecular orbital theory. Valence bond theory considers covalent bonds as being localized between a pair of atoms, resulting from the overlap of atomic.
Okay, so we have discussed just now that in VBT, valence bond theory, it is an overlap of atomic or hybrid orbitals, okay, forming a sigma bond or pi bond, okay.
Orbitals or hybrid atomic orbitals. This overlap results in sigma or pi bonds, and we can use this theory to predict molecular shape. However, there are
right. Okay, so this is another useful tips for when using valence bond theory. We also can predict molecular geometry, tetrahedral, trigonal, pyramidal, and so on. And we will discuss this later.
Simple molecules that do not conform to this theory, like the diatomic oxygen molecule. Given this Lewis structure, where each oxygen atom has a full octet,
okay, we will discuss about this, why oxygen, O2, was not properly explained by valence bond theory, but was able to be explained by molecular orbital theory. But just KIV this first.
Expect oxygen to be diamagnetic and weakly repel a magnetic field. However, it does in fact exhibit paramagnetism, as liquid oxygen is attracted to a magnetic field. To explain this, we have to turn to molecular orbital theory, which differs from valence bond theory in that electrons are considered delocalized throughout the molecule, and atomic orbitals combine to form molecular.
Okay, so now if valence bond theory is explaining about the overlapping of atomic orbitals, forming hybrid orbitals, and there's a overlapping of probably atomic and hybrid orbitals to form the covalent bond. And another thing that we have to remember, that valence bond theory only involve valence electron, okay? For molecular orbital theory, the theory does not view in terms of atomic orbitals. It views the molecule or the compound in a form of molecular orbitals. So remember the first topic, we have learned about how to do electron configuration in atomic orbitals. So the same principle is used to arrange electrons in molecular orbitals. Okay, so please revise back on the three principles. So let us move on.
Orbitals, which are also delocalized throughout the molecule. These can be sigma and.
So we stop here. Important for you to understand these difference first. One is valence bond theory, considering only valence electron only, whereas molecular orbital theory considered the total number of electrons, okay? And one is VBT explained about the overlapping of atomic orbitals, and which form a new hybrid orbitals. Whereas the molecular orbital theory view the compound or the arrangement of electron in a form of molecular orbitals right away. Okay. Now remember about the valence bond theory. And let's say if you have CH4, and remember carbon has to accommodate 4 electrons from hydrogen. Okay, so carbon has to rearrange the orbitals so that it can accommodate 4 electrons from hydrogen. So how do we solve that?
As it tends to do, it will take its 2s orbital and all of its 2p orbitals to create 4.
Okay, it has to take the 2s orbital, meaning that the carbon has to take the 2s orbital and the 2p orbital, okay, form hybrid orbital called sp3. So I repeat back, carbon, considering the valence electron only, take the 2s orbital and the 2p orbital, forming, from here, atomic orbital, forming hybrid orbital, sp3, to accommodate electron from hydrogen.
sp3 hybridized molecular orbitals. In order for carbon to hybridize its orbitals, it must first promote one of the 2s electrons up to the vacant 2p orbital. Then,
right. So this is a very important concept. In order for carbon to accommodate electron from hydrogen, it has to provide empty space, 4 empty spaces. Okay, remember that electron has to be shared, has to be paired. Okay, originally it was like this, right? The configuration for the valence electron for carbon is 2s2 and 2p2. So there are only 1 and 2 spaces. So in order to accommodate 4 electrons, okay, so the carbon
electrons up to the vacant 2p orbital. Then it can hybridize them, leaving 4 molecular.
Okay, now you have a new orbital called hybridized orbital. Why it is sp3? Because it's a combination of s, 1s, not 1s, it's 2s, 1, 2s, okay, and another 3p. That's why it is called sp3.
Orbitals that are identical in energy or degenerate. Each of them has 1 electron, leaving room for another that will be provided by the other atom.
Okay, so now you can see the red one. So the red is electron from hydrogen, okay? So red is electron from hydrogen. You can see now the carbon has enough space to accommodate the carbon orbital, the valence, has enough space to accommodate electron from hydrogen, the 4 hydrogen, okay?
Participating in each covalent bond. Every energy level has 1 s orbital, 3 p's, and 5 d's. And the number of bonds an atom can participate in determines the number of atomic orbitals that will need to be hybridized to form the necessary molecular orbitals to generate the bonds. An sp3 hybridized carbon is typically participating in 4 sigma bonds, but carbon can also be sp2 or sp hybridized.
Okay, so take note, CH4 just now, because we need, the carbons needs to accommodate 4, so it will form sp3. But remember, carbon also, there are sp2 and sp.
Let's look at an sp2 carbon.
Right.
If it is sp2 hybridized, it has just 3 electron domains, which can happen if it has a double bond to something. Take C2H4, for example.
Right. So C2H4, okay? So these two are carbon, and this gray are hydrogen. We only need to discuss half of it because the same hybridization will be used for the right side. So it's either the left side, carbon of the left side, or carbon of the right side. The hybridized orbital will be the same.
These carbons is sp2 hybridized because of the double bond present. What this means for molecular orbitals is that...
Okay, now you can see the same principle is used. Okay, originally the valence orbital, okay, the valence configuration is 2s2 and another 2p with single electron and an empty orbital. This is the original before it is hybridized, okay?
The carbon will promote 1 electron
again, and then the electron from here is promoted, forming degenerate orbitals. And then you can see now you have 4 empty spaces, right?
And take its 2s orbital and just 2 of the 2p orbitals to generate the sp2 hybridized orbitals. That leaves 1.
Okay, so this is very important. If CH4, you need to accommodate 4 electrons. Okay. Now, if you look at here, because we are talking about the left side only, this carbon needs to accommodate 1 electron from hydrogen, this hydrogen, 1 electron from this hydrogen, and 1 electron from the right carbon. Okay, so I'm talking about the left. So 1 electron from here, 1 electron from here, and 1 electron from here. So 3 electrons now needs to be accommodated. Okay, so previously CH4, 4 electrons. So in order to accommodate 3 electrons from this hydrogen, and this carbon, you only need to provide 3 empty space. So that's why the combination of S and 2p, it is enough. So that's why the hybridized orbital is only sp2, not sp3. So what happened to this?
P orbital unhybridized. It is the overlap of these unhybridized p orbitals.
Okay, so it is called unhybridized p orbital. Okay, so this is where the unhybridized p orbital is placed. Okay, remember that the p orbital we have used in sp2, 2 p orbitals has been used in sp2, leaving 1 p orbital unhybridized. And this unhybridized p orbital will form the pi bond, okay? Because this carbon has pi bond. The bonding between this carbon and this carbon has a pi bond. So one unhybridized p orbital will form the pi bond, meaning that this carbon has one unhybridized orbital, and this carbon has one unhybridized orbital. So if you can imagine it in a 3D form, the clouds of electron is overlapping, forming a pi bond.
Each containing 1 electron, that generates a pi bond, which is what the second bond in this double bond is. The p orbitals extend in perpendicular fashion from the plane of the molecule, and they overlap to make the pi bond. The same goes for C2H2, which has a triple bond between them.
Right. If you have C2H2, now imagine the same process.
Each carbon has 2 electron domains, which means it will be sp hybridized. After promoting 1 electron, it needs to only utilize the 2s orbital and 1 2p orbital to get the sp.
Right? Because you only have to accommodate electron from hydrogen, 1, and electron from the right carbon, the right side carbon, 1. So you only need to provide S and P so that you can accommodate electron here as well as here. Okay? But what happened to the other 2 P's?
Hybridized orbitals. That leaves 2 unhybridized p orbitals, each with 1 electron. In this case, they will generate 2 pi bonds, one from the overlap of these.
This happened because now you have triple bond. So you have 2 double bond. Okay, so you have triple bond here. So now you have 2 sets of unhybridized p orbital from each carbon, forming the pi bond.
P orbitals, and another one from the other set of p orbitals that will extend perpendicularly from the first pair. What you end up with is a linear molecule with this propeller-like orientation of the unhybridized p orbitals, which form 2 pi bonds beyond the initial sigma bond, which is the...
Right? Okay. So very important for you to understand the definition of valence bond theory, how it views the formation of covalent bond in a view of valence bond theory with regards to molecular orbital theory. So the keywords are in valence bond theory, considering only valence electron, and atomic orbitals are overlapped, okay, forming a new hybrid orbital. Okay, right. So we will discuss molecular orbital, and also we will discuss how valence bond theory or hybridized orbital can be used to identify the molecular structure.